Hello. Sorry, I have been on holiday for the weekend. I think this is working. Yep, appears to be working. Yeah, and I just going to continue now on the schematics. Maybe do a little bit of layout alongside because that helps determine some parts. I've been through the hardware design document, but I'll leave it there. And I want to check alongside the Metro schematic to make it similar. Here's the data sheet. Something I was thinking about, last night. What happens if we use more precise resistors than 1%? Are the prices any different? For example, what happens if I used 100k resistors, 0402, and they were 100k and they are 0.1 precise? Are they expensive? 1p, quite expensive. Not terrible. I was just thinking because these inverting amplifiers can be up to 2% off. Might be quite nice that they're 0.2% off, but I don't know. I think in my next video I need to find some text. I need to really think about how I have these anti-oscillation capacitors in, like, where are they really needed? Why do I not have them on the outputs but I've got them on the inputs? Because I think the main problem is actually with oscillation is the driving output that creates oscillation. And if we have these resistors, I know there's another way. I'll have to do some research and then I'll start before I'll do it. But in this one, I think I'm just going to do a bit of layout and try and match. I want to match the SD card, the USB host, the power supply, it's interesting, I'm using just because I was using them elsewhere, my 3.3 volt power supply is a SPX, which is a low noise one, but it doesn't have a ton of power output. The main thing to look at when choosing a regulator is think about how much current it needs and what its thermal resistance is. So this is is it SOC 23? Yeah. It's just got interesting, this Sweek version. Oh, the DFN8 version is really good. Interesting. What's that? What's the DFN8? It's like a Sweek with a thermal pad in it. Because we RP2350B power. I wonder if anyone's done benchmarks yet. I guess it's in the data sheet should tell us. See, this is what you have to do when you're designing power, especially, is to think about how much power your microcontroller is going to be pulling and what the voltage drop is going to be for the regulator. Thermal characteristics. Solid profile. Oh, I thought we were in the specs. Here we go, electrical specs. What I'm looking for is, they did used to have maybe imagining it like an estimation of power. Power consumption. So here's for everything. Power consumption in typical use cases. Gives you rough ballpark. Oh, and they're the codes. Will probably be like hello ADC sort of range. So say the worst one with the USB running is 52 milliwatts total. So what's that? 52 milliwatts. That's 0.052 watts divided by 3.3. Huh. It's 15 milliamps. So that should be fine. I mean, it's going to be powering. Wait, I'll go back to this one. It's going to be powering a. Oh, it's also going to be powering these chips, the flash chip, and it's going to be powering. That. But then I've got this. I put in a separate one for the MCP 4728, and it literally just runs straight off the 12-volt rail. Because I don't think the MCP 4728 don't know if we'll get any power consumption ideas from this data sheet. So it gives you a sometimes you can get things from the description at the beginning. supply current with external reference, supply current with internal reference, maximum 1.4 milliamps. That's pretty low. So I made a completely dedicated chip for that, but it's going to be dropping 12 minus 3.3 equals 8. I should use an on. So I've got 12 coming in. 3. So there's an 8.7 volt voltage drop, and I don't really know. Is this giving you note 1? That's with it unloaded. We're not going to load it very much because we're putting it straight into an op amp. So say 2 milliamps. So it's going to be 0.174 watts. And we've got 191. So basically to find the junction to ambient, so basically the internal die to the ambient thermal resistance is 191 degrees per watt used. So you just times that by 191. So it'll rise 3 degrees. And so it'll rise 3 degrees above ambient temperature, or whatever temperature it is at the moment. So that is fine. And that's with the rails tied high. But here, in this one, we're driving an SD card. I wonder if we just add another one for an SD card. So we'll pull this off this net and it'll have its own dedicated net for the SD card. So the micro runs off this power supply. The micro runs off that power supply. The flashes and the microcontroller run off another power supply. Oh, I've got the screen as well. No, I don't know what the screen we're using is. Oh, this is all very confusing because I've got the I wonder if the power supply for the screen should be next to the screen on this board. Sorry, you can't see that. On this board below. Again, I'll just copy and paste. Yeah, that's interesting. Maybe I should share the SD card and the screen on the same power supply. We'll call it something. Call it 3 volt 3 screen SD. Oh, that's the label. that also powers that. I'll put it next to it so it's where I'll put the screen is there, the ST next to it. This is all currently on this. Where is it? It's not even on the board. So no, this is different as well because this has got its own board. So I haven't actually explained this yet. Vertical sockets are quite hard to come by. There's only one manufacturer that does a vertical SD card socket. And as an experiment, I'm going to have I'm going to get the standard SD card socket, and it's going to pretend to be a vertical socket with a connector that's going to go into the jack board. So this connector here let's call it, oh no, I've done it already. This is a 2.54 socket, or it might be something different. Seems like I left myself a note. With the LCSC number. It's basically a corner header, but it's 1.72 pitch. So this is on the jack board. Oh, this is a value. That's the jack board. And this is going to be the SD board. Maybe using that connector. So the power will come in this side from the jack board, and this is on the jack board too. So I actually need 5-volt jack. So the power comes in through the FFC connector into the regulator, which is on the jackboard side. Oops, sorry. So it's comes through the ribbon cable on the jackboard side and comes to the connector here for the SD card and to the display I've done that already. Might try and make it look clearer by like that. It's going to be quite a lot of current though, so what's the screen called again? The screen is NV3030, maybe. Its current, roughly, its current consumption is probably going to be quite a lot because it's a bright LED. This is its 3-chip white LED. 60 milliamps, but there's 3 of them, so it's 3 times 60 milliamps. That'll be the main power consumption of it. So that's 3 times 60, 180 milliamps. Does it run off? Does it run from 5 volts or 3 volts? Or can it run from both? Input voltage 3 volts. But then the LED oh, this is the internal schematic of it. Oh, interesting, it's just anode and cathode. And it's 180 milliamps. Oh no. It doesn't have an LED input, so it just, you put 3.3 volts in. I'll go straight into the anode, and the cathode comes out. It goes through a 10 ohm resistor to ground. Through a 60 milliamp. That must be a powerful resistor, because that's, was it? The voltage drop is maybe 2.7 volts at worst. 3.3 minus 2.7 volts. It's a 0.6 volt drop. And it's how many times 0.06? Oh, it's not terrible. So the LED just has to be 36 milliwatts. Right. But we don't have to, it's not an anode and cathode, it's got its own built-in resistor. But it needs 3.3 volts. It can't. I mean, you could do 5 volts, but if you did 5 volts, it would probably overdrive the backlight, and the resistor would get really hot. So our total current is going to be. How do I know how much current an SD card? here's someone who's experimented with power consumption. That's pretty typical. That's the data rate. Wait, is that about power consumption? Yeah, performance and power consumption. Here we go. In spy mode, maximum was right. It's 400 milliamps. It can't be true. But briefly, oh, it's like pulsing. Typical SD card consumption is 30 milliamps in SPI and 100 milliamps in fast mode, which you might use. So it could be average 100 milliamps, which is quite a lot. So it's good we're coming in with 5 volts. Because if we have 100 milliamps, so if we have 5, so we worked out before that we had, wait, sorry, we worked out before we had 180 milliamps. So we have 180 milliamps on our screen side. Oh god, this is going to be quite high. Maybe this is going to have to be something else. 180 milliamps on that side, and they reckon in quad, in 4-bit SD mode, it could be 100. So we could almost be having 280 milliamps times, what is it? 5 minus times 280 milliamps. Could be half. It could be half a watt. That's way too much. So I think we might actually have to here. I'm reluctant to put in another switching supply, but I could put in the, like they've used here, the best thing to do is go to jlcpcb.com with the parts library, which we're going to be using, and then go to power management, voltage regulators. What's any basic parts we can use? Yeah, here you go. That looks like a good one. That's 5 volts. 30 volts, 5 volts. Oh no, wait, sorry. 3.3. 5 volts. That one could do an amp. That one needs 100 milliamps. So probably want this. Wait, do SD cards run off 5 volts or 3.3 volts? I don't actually know. SD card voltage. Three volts. So we'll just use this because if you look, it says it can do an amp, and if you look at we're going to have 0.476 watts, so almost half a watt. And this is the SOT223 package times 90. So it's going to be like, oh, even that's a bit warm. But that's the SD card is average. The LED supply is going to be a constant. Oh no, wait, that was wrong, sorry. Oh no, it's one. Say if it wasn't the SD card, it'd be 1.7 times 0.18. It'd be a constant 300 milliamps. Because LEDs are always on, you know, they're a constant draw. And was I looking at the junction thermal resistant to junction ambient is 90. So it could raise 30 degrees. So it'll get quite warm. Oh, this is where I need an a switching power supply. Could I just use this again? TPS 54302 or what's this one now? I'd rather not add another special part. Need to just use what you have already. It's quite cheap, it's 30p. What speed it switches at? Could just add another one of these, and it uses it's adjustable output, so yeah, I think that might be the better option. I'll copy it again, but it has to be I wonder if I can. I'm adding another switching supply there, which is a bit annoying. And this, now because we're switching, I might just take the 12 volts in. I'll have to work it out later. Good if I could use the same inductor. I'm not sure if I can. That'll be much more efficient. And we can both use that to drive both the screen and its output goes down to 3.3 volts, doesn't it? Max recommended application output voltage. Yeah, goes down. And the input I'll make from the jack board. Oh, we're not running 12 volts into the jackboard. Because the input barrel connector's on the microboard. So we'll make one board. That will give us a nice healthy dedicated power supply for the SD card. It's becoming very messy very quickly. I'll have to think about those capacitors, and I'll have to adjust that voltage divider to make it 3.3 volts. Probably don't have enough time to look at that now. With the equation. Feedback divider. I might have to do a dedicated video just to this. Oh, but here's some recommended parts, values. Just copy this for now. The odd thing is Adafruit was using a 3.3 microhenry inductor for 5 volts, and they recommend a 10, so I'm not sure what that was about. They recommend for 3.3 volts 100k for R2, which one's R2? The top one. We'll do that. But really I need to do like a analysis on the whole thing. This one's going to be 22k, and it reckons a 6.8. I need to crunch the numbers, but there's not enough time to do it in this video now. That'll give us roughly 3.3 volts, and it should be. So because this isn't a linear regulator, we can't do that equation where we did the voltage drop time the power times the thermal resistance, because basically it's pretty much you might get don't know if you get any efficiency graphs, but here we go. No, but roughly usually here we go. It's quite handy. 12 volt in to 3.3 volt out. The efficiency, we'll be up at the 100 milliamps ish range around here, is like 90%. So if you're using 200, so if you're using like half an amp somewhere here, oh, press the button on my mouse. So if you're using half an amp, which is probably, it's a logarithmic scale, somewhere here. It's going to be 90%-ish efficient. So only 10% of it would be wasted on heat. So say if you, I guess you could say if you're using half, or if we were using I worked out we needed half 0.47 watts, and we were getting 90% efficiency, then we would need, what was that about? Oh, clear, go away everything. Clear. Master reset. Clear everything. Clear, clear, clear. We're using 0.47 watts. We would need, well, no. And we were 90% efficient. Yeah. So we would need 10% more than we. That's not quite right, but. We would only need basically we'd only need half a watt, and from 12 volts, from 12 volts, yeah, we need half a watt at 3.3 volts, right? So half a watt at 12 volts, so half a watt divided by 12 equals 41 milliamps. We only need 41 milliamps. It makes it much more efficient. The only downside is we're introducing more switching circuitry, which is A, complicated, and B, can create interference. But now we've got a switching circuit on the screen on the SD card, dedicated to the screen SD card, a linear power supply just for the microcontroller, a linear power supply for the analog to digital converter. I haven't shown this yet. I've got a voltage reference for the microcontroller's ADC. The digital to analog converter doesn't actually seem to just be running off the same as the microcontroller. The audio one. So I don't know if that's great. Oh no, it isn't. It's running off the same as the input. The input DAC and the input ADC and the output DAC of the audio have its own dedicated power supply, and there's a dedicated power supply just for the I2C digital to analog converter. And what that means is it also helps with layout, so I can put these are quite small little SOC23 power supplies, so they can be put really close to their dedicated partner. So I'm not running 3.3 volts all over the board, you know. Yeah, so that's the kind of the power supply thought out. I need to do a thing. Oh, and then I said what I was going to do this time was I was going to get the I/O fitted. It's the inputs and outputs. This is the USB host. Let me just check that. I want to do exactly the same. I don't want to copy this switching circuit stuff, but I want to do a very similar thing here to here, where the USB host is sitting on the jack board, so it gets 5 volts to the jack, and then it gets the USB host outputs. They've put pull down resistors. I need to work that out. And they have it so that the power is fused, which is probably a good idea. Am I using any fuses? I might put a polyfuse. It is a good idea. That's a really good idea, because we don't want this output to short. to when the output shorts, we don't want it to pull everything down with it. You know, we want it just to turn off. They've got USB H power. I wonder what that is. They've got an ability to switch off the 5 volts. Is it from a from a GPIO? I mean, that might be handy for resetting your device. It's funny that they've got it with 2 MOSFETs to invert the output. Oh, it's because it's high side. Yeah. That's clever. I'm going to put that in, I think. I'll need to choose the resistors. I'll need to choose the MOSFETs later, but I think they're called NFET. No, they call it NMOS, I think. Just general. So we need so it's high side, so we need a PMOS. I'm using a PMOS. Wait a minute. I'm basically stealing this straight off Adafruit. I'll have to double check the so basically we have a P and an N anyway. I'll have to check if they can. I'm not sure if they'll run very well with 3.3 volts. Was it the A3400? Where's my mouse? Come on. What? No. It should be a basic part. Oh. I thought the basic part. Oh, transistors. Basic part. Come on. Yeah. A3041 is the P-type. Yeah, for some reason it didn't come up. A3, oh, it's because of A3400A. But the gate threshold voltage is 1 volt. Great. So basically, we want to turn the 5 volts on and off to the USB host, but we're doing it high side because we want to turn the 5 volts on and off. We don't want to turn the ground on and off because that could be really dodgy, because it can find ground through other connections. So it's always best when you're turning a device on and off is to turn its 5 volts on and off. The problem is the gate has to be to turn on. The gate has to be above the gate threshold, below the 5 volts. Wait, that's the wrong way around. So, and the output of the microcontroller is 3.3 volts, so you can't do that. So what you have to do is what Adafruit have done here is you've got a low side switch turning on a high side switch. You need a resistor. What is it, 10k? Yeah. So this will hold that on if that is off. And then interestingly, they have another pull-up, but I guess it's because you don't want your USB host device because the GPIO can change states when the microcontroller turns on. So I think that's a good thing to copy from the Adafruit Metro design, is that we have the ability to turn the device on and off. It could be used for either they called it USB power. I'll call it USB-H, USB-H and enable. Let's call it USB-H power enable, and it's when it's on, so it's enabled. It's enabled when it's off. So we'll make it a just so we can keep our minds. So the USB host is fused, can be turned on and off, and I should probably put on the termination resistors, aren't they? I'm not sure about that. I will also put them in, but I don't know what their values should be, so I'll remove their values. And I'll make them do not populate currently. But they're there just for a reminder for me to think about it later. think they're for it's like a transmission line thing. I can't be totally sure. It's not for CC because that's on the other side, and this is just a USB-A, so it's not like a USB-C thing. Now we've really got to think where all these GPIOs are going to go. All of these are going to get used. How do I do that? Yeah, see, this is the new thing with KeyCAD. If you drag left to right, does one thing, and if you do right to left, it does another thing, but I can't work it out. Let's just delete that. So we've definitely got the PSRAM chips select on GPIO 0 because that's where the hardware secondary flash can be. And we've just created a new, but we want to know where that needs to go because it's going to be identical to the Metro board. Which is GPIO 29. I will probably end up deviating from this, but I just want to start somewhere that's common. What else is unique? The SD card. What's their SD card labelled? Yeah, it's here. What have I called the SD card? Oh, I just call it DAT by its DAT names. I should really call them. So DAT 2, DAT 1 and DAT 2 are extra pins. Clock is the same really, so I don't care about that. But Mozzie and Command are the same. Oh, I can't use thingies. I'll just do that. And these are on GPIO 33. So the clock is on GPIO 34. Command is on 35. DAT 0. Imagine these are going to go in order. It's 36. DAT 1 is 37. Because there isn't a SDIO peripheral. So imagine it will be a PIO. DAT 2, 38. 39 is DAT 3 / chip select. Okay. So I'll delete those from here because these are the ones that I had originally. Right. And they have I have a stemma QT and they have a stemma QT connector. Where's my StemmaQT connector? Here. StemmaQT is a connection system that Adafruit and SparkFun, which is called I2C, no, which is called a Quick, QWIIC. They're pretty much the same thing, which is like a connection system for I2C, and it's quite handy if you want to, like, I thought it'd be quite cool if you could connect dev boards around the back. So I'm going to have a dedicated I2C pin port peripheral for that, and so do they, and it's called, they just call it SDA SCL with 10k pull-up resistors. That's interesting. Maybe I'll do that. Get those 10k pull-up resistors. This is because 3 volts. This is because I2C is uses switches on the data line to turn it on and off, so you can connect many to many. So yeah, and they've put them, so my stemma, it's only 2 serial lines, one's a clock, one's data, and it's pin 20 for the SDA. And the clock is 21. Yeah. So that's stemma. Now I've got gates in, switches, encoders, all of them are general purpose. I2C, what I need to do is look at the data sheet. I wonder if there is a... It isn't one of just... Oh yeah, it's in the data sheet, isn't it? Top. No, but that doesn't tell you the different peripherals. It does here. So we've used one I2C in GPI 20 and 21, which is I2C 0, because there's 2 peripherals for each type. So this is just for a note for me. That's I2C 0, and we have one more I2C for my I mean, these can be anywhere really. So I guess the best thing to put in first is something that, because what I want to do, I want to put the display where the HSTX can get to. I know that it's not a DVI output or anything like that, but in the Raspberry Pi examples they did, for the HSTX interface, they did do a SPI example, and I was wondering if maybe you could get SPI to run quite fast on with the HSTX peripheral. So I think I'll just put it there, but these are DVI, you see. $12, $13, $14, $15. I'm just going to put it where Adafruit puts it. But on this, I'll call it on this side, I'll call it the HSTX pins. So I'm not quite sure what I'm doing here, but so it seems to go from 12 to 19. Ooh. The thing is, we've got a display. Why is it I²C? Huh. I thought it was SPI. Oh no. Yeah, 4-wire SPI interface. 4-wire. But then if you look on the board, it's only showing SDA SEL. Which is odd. For SPI. Oh no, they have the same connector within them. That's not 4-line SPI, that's I²C. Why are they labeled SDA SEL if they're 4-line SPI SDA SEL? Yeah, the components of I²C. Here we go, on the Arduino forum. I'm looking at using one of these displays. It says 4-line SPI, but only has one SDA line rather than separate SDI and SDO lines. Ugh. We can find a bit more information. Might be worth. I think it might be worth. Oh, there's one here by Waveshare. They're quite good. They call it DN and clock. I'm gonna guess SDA is DN and so I've got clock. Should we call it? No, we'll call it SDA, even though it's SPY. It's confusing though because of 12th. Right, I'll connect these up. Don't think I need this many pins though. Because in Pico examples, it's the official examples, and if we go to HSTX, there's a SPY LCT example. Let's just copy that. So we'll do 12. Because it's 12, 13, 14, 15, right? GPIO. Yeah. I'll just copy it from Pico examples. We can run that code from Pico examples to verify that we can get the HSTX to work. And I might also look. We'll put HSTX 12 underscore DN HSTX 13 underscore clock HSTX 14 underscore chip select, and then I'm guessing the last one is command, what it was called? Yeah, DC. And then reset and blank, even though they're not really being used by the HSTX. Wait, that's 17. It just shows me where the HSTX interface is. And what I want to verify is GPIO 12 yeah, that's right, I think. Oh, chip select 13, no, that's wrong. Clock HSTX. Give you any rules about how it can be any permutation of HSTX capable pins. So any order. Okay. So what I want to do is I want to make sure that if I just use the SPI peripheral, so I actually want it's called DN, but it means DN of, so it's, is it TX? So SPI 1 TX is on HSTX 15. I wonder if I should put some resistors here, 0 ohm resistors in, so I can fiddle around with them. The clock should be on 14. The chip select, it's not so important, but it should be on 13. And DC, well, that's more of a display thing. I guess it's on 12 then. So we can fall back to the SPI interface if we want to, which has SPI 1 here. And they need to go. I've broken my naming convention. So DC is here, blank is here, reset is here, data, guessing is SDA, clock, the chip select is there. See, it says SDA, SEL, but yeah, there's those. So I can delete all of those. Now, this board doesn't have one of the audio DACs on it. Does it have anything else that I'm going to be using? I'm not using the QSPI interfaces in the same way. I'm using the SD card in the same way. Could be cool to put a NeoPixel in, but I'm not sure about that yet. And power supplies are different because we're running from 12 volts. Yeah. So only similarities we've really got is the power supply that gets us down to 5 volts. The SD card's in a similar place, and I've copied the and these are called MCU gate in, aren't they? Yeah. So, so we've got scale. We've got to get our DACs in, our built-in DAC. So it'll be Interestingly, I can't see it there. It'll be our CVN1, CVN2, CVN3, CVN4. I'll just whack them there. I've actually got 4 more ADCs. I might just have a little look at the data sheet. So GPI 26, 27, 28. Huh? What? Oh, where the QFN 80. It all just goes into one mux. They've removed spikes in nonlinearity. So I'm using the first 4, but then there's a whole load of spare ones. Okay, it's a successive approximation ADC, runs at 48 megahertz. It's about how to program it. It's got its own power supply pin, that's what I should do next. These are its registers. Does the hardware design board talk about ADCs? No. Might as well just use the first 4. For neatness, I could just put the gates there. So these gates. There are little things about driving SARS. Driving the analog inputs of a SAR ADC. Effects of input source resistance. Errors due to pin capacitance and leakage are minimal. The accuracy of a SAR can be compromised if it's not given enough time to sample. Impact of an operational amplifier. Op amp noise, filtering. Could do filtering. That's what these capacitors could be useful for. Reducing the bandwidth into the ADCs. That's something to look at later. I can't be bothered to do this now, but I have an ADC, a reference, voltage reference that comes from the 5 volts. I wonder if that should come from the 12 volts into VREF ADC, which should drive this pin. Oops. It's probably a good idea to put in a decoupling capacitor too. Not sure what was happening there. I've got it going, I've made a negative voltage reference as well. I really should use better op amps. I'll get onto that later. I might also adjust these feedback capacitors here to think about it. And then the next thing is I need to find another place for my slow DAC outputs. So we need I squared C1. Put it next to the other one, because it's at pin 2021 by I squared T0, and then 2223 got some other GPIOs ready, busy. Can't remember what that's. Let's look at the pin descriptions. Oh. This is a status indicator of the EEPROM programming activity. Do I really need that? And LDAC. Synchronization is used to transfer the contents of DAC input register to the output registers. Not sure if I really need those, but I'll just leave them in anyway. Do they need note 1? Yeah, it needs pull-up resistors as well. I don't know why I don't have pull-up resistors. See, this is how designs get really complicated. So, okay. Now I've got my DAC connected. I haven't got any outputs connected. The switches, encoders. I2C interfaces. Oh, I2S interfaces. I mean, I could just go. This is just going to be on a general purpose. And I see we've run out of space now. But to be honest, the DAC can go here. These are just configuration pins. So I can stick those like that. These can go here. And this can go here. I might even just get rid of that. Is it the PCM? Leave that for now. And we've got some switches. You know what, this doesn't have to be in the same place. Just dump these here. Lovely. These are just switches. These are for these encoders up here. Encoder 1, encoder 2, and there's a switch on each one. Oh, I've used up all the GPIOs now. Whoa. Now there is on the chip select on the this thing. Is that right? I might just double check the hardware design flash memory. Yeah, so there's a USB boot. Look at the complete schematic. The chip select. Yeah, so what I want to do wait, no, this is the boot pin. Where's the reset pin? It's the run pin. Things I've run out of GPIOs. That doesn't matter. So I've got 2 user switches on the front panel, which is going to be these ones. But I also think I want a menu/boot one. I've run out of GPIO. But what I could do is delete those useless, like, ready busy. We don't need ready busy. Where's ready busy gone? Perfect. So we can put user 1 and 2 there, and we call this one user 3. User 3 slash boot. Well, let's call it menu boot. So the idea is when it's running, you can press it and it might show up a menu, so you could run different programs. Or when it's off, or you press the reset button and you hold it down, then it's to reflash the entire system. There's a run. A run switch as well. Let's try and find it. There's the switch, which is menu/boot. Oh, I called it. They should all be enabled when down. This can be called this. So when you hold that down, it resets the chip, the flash chip. I wonder if that might cause problems, I don't know. So we're going to read from the GPIO if the program's running, or it'll, yeah. But I need to find the other switch, which has probably disappeared, or it just doesn't exist. Doesn't exist, which will be our, doesn't need this, which is going to be our run. This will just reset the whole microcontroller. So if you press the run button and the reset button at the same time, it puts it into flash mode, into a blank mode, basically. So that's actually SPY 1 or HSTX. So I want to experiment to see if I can make a really super fast SPY interface for high refresh rates. I don't know if it's possible, it's just an idea. And then we've got an I squared S DAC. And we've got an I squared S ADC. No idea if I can get all these running all at the same time. I'm going to run out of PO interfaces. And that's it. I guess I could label these switches. Oh, and the other switches. I should put all the switches together. So I have a run switch, a reset switch, 2 encoders, and have I just lost the other switches? No. Here they are. Oh, and there's the leftover. So all my switches are together up here. I have 2 general user switches. One that works as a menu-ish switch thing, and then I have one that sits next to the USB connection to reset the micro. Yeah, I think that's a good place to stop. I need to verify that all this is correct. Wait a minute, did I put my... No, because my analog outs come from a ADC, DAC, so it's only a serial interface to get to them, and yeah, it's 2 serial interfaces, so I don't need to worry about that. Wow, what about my gate outputs? Ah, no. Got 2 gate outputs that need to go in. I think I should get rid of LDAC. I've got no LEDs either. What was LDAC again? Synchronization input to transfer the contents of the DAC input register to the output registers. Is it needed? This pin can be driven by an external device. Transfer the contents of the input registers to the output registers and to select device. When the logic status changes from high to low, the contents of all the input registers, so it updates the outputs. If it's permanently turned to low, the contents of the input register transfer to the output registers immediately. Yeah, I don't need to synchronize them all. So naff that, and we'll just tie that one low. I'm not going to connect that one. So what's that? LDAC. It's off. We've already got rid of ready busy. We need to find one more pin. There's all these strange, useless things. Like, do we need to put on the PCM 5102? I mean, if I really needed these configuration bits, I could put an I/O expander on it, but So what was it? Oh, I only really have mute enabled on that. But mute might be quite handy. Where's mute? It's pin 17. Soft mute control. Might be quite good. I've got more tat on the PC. Yeah, audio interface mode. What else did I put in? Format selection. I just wanted to leave the options open, but bit clock. Audio data out. Audio interface format. I think I might want to change those because I don't know which mode's best. What about format? I2T 24-bit. Let's just make that one a resistor. We'll just make it low. So what's that format? Didn't I do that one? That's oh, it's not there anyway. Oh no, wait. Mute. Left for o'clock. Oh, I've really got rid of it. I've got rid of it by... it's just floating. I'm going to ground it. Although I'm going to ground it. No, I'll just leave it like that, yeah. But annoyingly... oh, there it is. So I've made 2 spare pins for the gates outs. I think I can't move those. I'll move this down here. And then I'll put these. So they're at least near each other. The funny thing about this is these are quite random locations, so I had to think about where I need to put everything when I start laying it all out. Anyway, that's the GPIO done. Anyway, thanks for watching.